In the last lecture, we discussed classical thermodynamics, which we said is a control theory, which is distinct from a dynamical theory, and which deals with isolated systems, which the user, who is an integral part of this kind of theory, puts together and allows to interact in various ways. We said that an integral part of that was simple systems, these isolated objects, atomic inside of the theory, which have no internal degrees of freedom, but only parameters that describe their totality. In this lecture, we're going to get a little deeper on that concept and start thinking about what a simple system means, both in the theory and how it corresponds to objects that we might encounter out there in the world. So I'm going to start us off with an analogy to classical mechanics. Recall that in the last lecture, we talked about the state space of classical mechanics. Let's talk about the state space for a given particle. Well, that state space is going to be the space of possible positions and momenta that has. Let's say that it's, for instance, in this case, R3 cross R3, where the first R3 is the space of positions and the second R3 is the space of momenta. Now, there's one other thing that we need in order to or I should say two other things that we need in order to say more about this theory. We need its initial condition, just as we said yesterday. And we need a rule that tells us how it evolves forward in time. In particular, that rule was Newton's second law. Now, the key thing to realize here is that F has a special role in this theory. We say it governs the theory in the sense that F encodes all of the information that we need in order to say what this rule is that tells us about the dynamics. F isn't the rule itself, but it does encode the information we need to get the rule. Now, let's try and analogize that to classical thermodynamics, which we've now had a little bit of experience with. In this case, our state space, as we said in the last lecture, is something like gamma 1 times gamma 2 times ... times gamma k, where each gamma is the state space for one of these simple systems that constitutes the whole system, or I should say makes a constituent piece of the whole system. We also need an initial condition. And we said that our rule was composed of the possible different operations, or I should say, the analogy of a rule that we get in this case is a list of allowable operations and their results. The allowable operations all made entropy either go up or stay the same. S increases or stays the same. And we talked a little bit about what those operations were in the last lecture. We'll get a little deeper into what they are in the next lecture. But the point is that S has the same kind of special role as F does for a classical theory. S governs the dynamics. Not the dynamics, but rather the control operations, because we don't have a theory of dynamics here. So this analogy should help us make sense of what's going on. In classical mechanics, this is what we would have for one particle. But what would we have for capital N particles? Well, each of these would just be raised to the n. And now we would have a sum over all of the particles oh, I'm sorry. No sum. But we would have a rule that the jth particle obeys, which might in principle depend on the positions of all of the particles. And let me say this is F sub j. Good. So now the whole set F sub j governs the dynamics in this case. In this case now, we have something like a set of n different state spaces which come together to form the whole state space, and an F which tells us how those sort of particles interact. In the same way, S is going to tell us about how these different state spaces, which we've numbered 1 through k, interact in classical thermodynamics. Now I'm going to clean up the board, and then we'll get a little bit into what these simple systems look like, both in real life and in our model. Okay, next, let's get to what a simple system is and sort of what our state spaces for simple systems look like. Now, in this context, I'm going to deal with the simple system as a model. We're not going to talk about how we would spot one in the wild until we sort of have laid the model out itself. So we said that a simple system has a state space gamma. And this state space is some kind of subset of our, let's say, M. Fair enough. That means that it can be described by M parameters. But with that being said, we need to figure out what those M parameters are. And to do that, we need to talk about thermodynamic variables and the kinds of variables that we'll encounter in thermodynamics. Okay, thermodynamic variables have at least 2 features. The first is that each one has a magnitude. And the second is that each has a type. Now, I'm going to use the term type here rather than unit, which typically would be used in this context. And all that I mean by this is that 2 quantities which have the same type might have different units. Type here being something like length, mass, time, anything of that type. So, for instance, 1 inch and 1 kilometer both have type length. And in this context also both have magnitude 1. All right, so in any case, these are the features, but in fact, there's more. Some thermodynamic variables have a third property called extensivity or intensivity. Extensivity. Now, it's important to note that within the model, there is no way that you can tell whether a variable will be extensive or intensive. There's nothing that you can tell that you can use to derive the extensivity or intensivity within the model. It's just something that you need to know. But when we make these correspondences to the real world that we actually live in, it's important that we know when something is extensive or intensive. An extensive quantity is one for which if we take our system and we make m copies of it, then that quantity will increase by a factor of m. An intensive quantity is one such that if we do the same operation, this quantity will not increase at all. So for example, if we have an object that has volume, let's say for instance 1 cubic meter, and we make 10 copies of that object, and we shove them together, the resulting mega object will have precisely 10 cubic meters of volume. However, if that original object was at 200 Kelvin, and we make 10 copies of the object and shove them together, the resulting object will still be 200 Kelvin. So let's sort of just diagrammatically show, what we want to do is take m copies of our object and consider, does variable x increase by a factor m? Now, we could also consider cases in which the variable does not increase by a factor of m, but something else. So let's go through a list of possible examples. As we already mentioned, volume of the whole object is extensive. Whereas we have a sense that temperature should be intensive. Density is another good example. However, consider something like length. If we take this object and we make 4 copies of it, and then we stack them, those 4 copies, side by side, certainly this length has increased by a factor of m. But notice that this length has not increased at all. Or maybe we could say has increased by a factor of 1. So which length do we pick? What happens in a case like this is that we don't have a well-defined answer to the question, and so we say that the quantity is neither extensive nor intensive. So this is neither. Okay, so with all of this in mind, now we can say that a thermodynamic variable has definitely magnitude and type, and possibly is extensive or intensive. And now we're ready to come back to our simple system and try to say what this state space looks like. So the state space always has m parameters. Because again, this was Rm. And one of those parameters, I should say at least one of those parameters, always has type energy. So we have one marked parameter with type energy. Which is extensive and is greater than or equal to 0. This parameter is called the internal energy. Now, above I said that we always have at least one of these parameters. There could be multiple. So there could be multiple internal energies in a general system. A simple system is precisely a system whose state space has exactly one internal energy. Good. Okay, so suppose that we're in this case. What about the other m-1 parameters? Well, it turns out that we can always use extensive coordinates for the remainder of the parameters. So can always choose m-1 other extensive parameters. And sorry, I shouldn't say m-1. But rather, if there are exactly, let's say, j of these internal energy coordinates, then we should get m minus j other extensive parameters. And these parameters are called work coordinates. All right, so now we've seen what the model of a simple system looks like, by which I mean we know what characterizes a simple system, in the same way that we know that an atomic particle in Newtonian physics is characterized simply by its position and its velocity or momentum. So that's fine, but how do we know when we see a simple system in the real world? How do we know if we see something that has these kinds of qualities? Well, we know, for instance, from our discussion in the last lecture, that a simple system should have no internal degrees of freedom. We should not be able to characterize one side as having parameters that we care about, which are different from the other side. So again, this is only going to be true approximately when we see it in real life. But for instance, if we have a large refrigerator, which is good at refrigerating things, then perhaps its whole inside is mostly at one temperature. So we could consider the internal volume of the fridge to be a single simple system. Another thing that we know should be true if we have, in particular, a simple system, is that there should be one internal energy coordinate. Now, this is where we need to use some of that kinetic theory intuition that I talked about in the last lecture. We know that what's happening, what this internal energy represents, is somehow the collected energy, the collected kinetic energy, of all the constituent particles that make up this system. Sometimes those particles are all allowed to share energy. And in that case, we have one well-defined internal energy. There's no way to split it up. But in other cases, only some of the particles share energy and others don't. So suppose that we take a box of gas and we put a partition down the middle of that box, such that it's very good at insulating the particles from each other. Then the particles in, for instance, the left-hand side of the box can share internal energy with each other, or I should say kinetic energy with each other. And the particles on the right-hand side of the box can share kinetic energy with each other. But the two sides of the box cannot share internal energy with each other. So this would be not simple. What we would say instead is that this system has precisely two internal energy parameters, one for the left-hand side and one for the right-hand side. Any system which is not simple, we would call a compound, and it can be broken into simple systems, typically. So we would have to make some choices, for instance, about how to divide the volume. But in this case, that's very obvious. Some of the volume comes on one side and some goes on the other. So we come down to the supposition, which we'll take to be axiomatically true, that every thermodynamic system should have a state space that can be decomposed into simple systems state spaces, such that each of those simple systems has exactly one internal energy parameter. And with that, I think we've basically covered what we need to start going on the control operations. I hope that at the end of the next lecture, we'll have a more complete picture of what simple systems are, what we can do with them, and how that helps us to model the real world. Thank you so much for listening, and I'll see you in the next one.